Just show you, I want to show you the father and daughter demo on the ice. I'm going to do it with carts and a spring. And then we're going to learn about systems. We're going to learn what systems are. And we're going to learn what kind of forces will accelerate a system. And then finally, I need to start introducing you to a free body diagram, the method you will use to do all problems involving force in the future. But let's go ahead and do this. So I've got a cart with a 500 gram mass and another cart with a 500 gram mass. They both have identical masses. And I've got a spring. And I put the spring in between them. And I compress the spring. Are the two carts experiencing the same force when I compress the spring? How do you know? What's that? Good, same mass, but that doesn't affect the force. Why do you say that the two carts are experiencing the same force?
Can I say that it
Sure.
might be different because your hands are like...
Okay. Well, I'm talking about when I let go of the two carts simultaneously, then what they are is in contact with a compressed spring. And I just want to make sure you guys are okay with them having the same force. Well, first of all, can I ask, is this scenario any different from a father and a daughter pushing off of each other? I just want to cut to the chase. Not really different at all. Whatever force this spring exerts on this cart exerts the same force on the spring, which means that's going to be the same force exerted on this cart, which means the cart exerts that force on the spring. It's the same force. They'll have the same force on them. Okay? How are they going to move? Tell me about the acceleration of the two identically massed carts. How are they going to move? You guys okay? Doesn't that look pretty much the same? You guys okay with that?
Yeah.
That's the same. Okay, great. I'm now going to replace this 500 gram mass with a 200 gram mass, a much smaller mass. Tell me, are they going to experience different forces now? No, Newton's third law does not become abrogated just because I replace the mass with a different mass. They'll still have the same force. Whatever force this spring exerts on this cart, this cart exerts on that spring, which is the same force that'll be exerted on that cart, which exerts the same force on that spring. Same force. But tell me, is one cart going to move faster?
Yeah.
Which one?
The lighter ones.
Yeah, the light one's going to move faster. So here we go. 1, 2, 3. Do you believe that the light one is moving faster now?
Yeah.
Why? Someone explain to the class, why does he move faster?
Because the mass is much lighter.
Good, because the mass is much lighter, which means when we consider both carts feeling the same force, one cart has a particular mass and a particular acceleration. The other cart has a way smaller mass, so a way bigger acceleration. Right? You guys okay with that?
Yeah.
Okay, great. Let me ask another question. What if I took this mass out? What if I now had this? How fast would that guy go?
Much faster.
Let's find out.
Zoom.
Oh, oops. Let's try that again.
Mr. Shana reaction time.
I know, I have cat-like reflexes. Okay, cool. All right, I just needed you to see that, to experience this idea that the big guy doesn't accelerate much and the light guy accelerates lots. Let's talk about systems. The first thing you should know about a system is it is whatever you want it to be, just like your hopes and dreams. It is whatever you want it to be. That's your system. So suppose I had a bunch of objects out here, okay? And I said, you know what? I want my system to be these three objects. That's my system. Doesn't it look like two eyes and an open mouth going, ooh? But anyway, so there's my system. Which means, equally importantly, not only have I defined what my system is, I've also defined what's not in my system. The rest of the universe is not in the system. There's several names we give for everything else. We call it the surroundings. We call it external to the system. We call it the universe. But if this is my system, everything happening inside the system is internal to the system. So there it is. You've defined your system and you've defined your surroundings. Let me give you an example of this in action. Suppose I'm driving my car and my car breaks down. So now I have to push my car. Okay? The problem is it's raining. It's raining. So I don't want to go outside the car to push it because I will get wet and I will feel uncomfortable. So I get a brilliant idea. I say, you know what I'm going to do? I'm going to stay inside the car and push against the dashboard real hard. And if I exert enough force, I will push the car. The car will move. Tell me, how many people think this will work? Yeah, of course not. Tell me, why not? Why won't it work? I'm exerting a lot of force. Why won't that result in the car being pushed forward? Yes?
The same and opposite reaction is like being done to the seat.
Beautiful. You guys okay with that? Newton's third law is coming into play. If I exert a big force on the dashboard, what's the dashboard doing to me?
Pushing back.
Pushing back with the same force, and those two forces cancel. So let's get with what Alexis was saying. Alexis is going, okay, but if I push on the dashboard's pushing on me, that means I'm going to get pressed into my seat. Doesn't that mean I could push the car backwards? Because now I'm exerting this huge force on the back of my seat. But the problem is, the back of the seat is exerting the same force on me. You see? There's no forces I can exert while I'm inside the car that won't result in an equal and opposite force that cancels it. Because what's the problem? Why am I not able to, accelerate the car?
You're still outside the system.
Thank you, because I'm inside the system. I need you to see that whenever there's forces happening inside the objects of a system, within the objects of a system, those forces are always equal and opposite because of Newton's third law. This guy exerts a force on this guy, and this guy exerts the same force back. You can't get any net force on a system from objects exerting forces on each other within the system. Tell me, what am I going to have to do in order to push this car?
Be surrounded.
Yeah, get outside the system. I'm going to have to exit the car, right? I need to exit the car. So now, if the car is my system, who's providing the external force to accelerate that system? I am, right? I'm pushing on the system. I'm external to the system, and I'm able to exert a force to accelerate the system. But let me ask you this. What if I considered the system to be me in the car? The system is me in the car, because we're both accelerating. I'm moving with the car. Now, what's providing the force to accelerate this system? It's not me anymore, because I'm part of the system now. Where's the external force that's accelerating the system? Yes, what's that? Who said that word, the magic word?
Friction.
Thank you, friction. Friction between what and what?
My feet in the ground.
Thank you. Friction between my feet and the ground, right? That's what's providing the force. My feet push this way, the ground pushes me that way. Friction between my feet and the ground are providing the external force. Tell me, what if I was on wet ice so that I've tried to move my feet but there's no friction at all? Am I going to be able to push that car? No way, not if the ground can't provide the force I need. So if I can summarize this in one statement, in order to accelerate a system, you need a net force coming from where?
Surrounding.
Yeah, the surroundings or outside the system or external to the system, okay? a force originating, I'm going to use like my English, a force originating from outside the system that is external to the system. A force originating from outside the system is required to accelerate a system. Okay. Whenever there's motion, whenever there's acceleration rather, whenever motion is changing, you can always ask yourself, okay, what's providing the force? What's the external origins of the force that's making that system accelerate? Like consider a child on a swing. You know that when you are 4 years old, you need your mommy or daddy to swing you. They push you, you swing a while, and then you stop, then they push you again. And that's what swinging is for little children. But soon you get old enough that you can swing yourself. You work the chains and shift the weight of your body, and you can make yourself swing as high as possible, and you don't need mommy or daddy anymore. My question to you is this: what's making you accelerate up and down? What's providing the force for you to start from rest and eventually be going really high like that? What's providing that force? Anyone have any ideas? Yes?
Your weight and gravity.
Okay, weight of gravity. Here's the problem. My acceleration is happening this way, horizontally. Gravity only acts vertically. So I'm going to have to say no. No, it's not gravity. Gravity makes you fall, but gravity is not going to accelerate you sideways. No, it's not gravity. So what is it? What forces are happening in this scenario? What am I doing? Oh, please. Someone tell me, what am I doing?
You're standing.
Well, I'm not standing, I'm sitting. No, I mean, what am I doing on the swing? What is the swinger doing? I'm so sorry, what am I doing? I guess that was confusing. What is the swinger doing? Sitting. And what else is the swinger doing?
Swing is me.
Good, which means, okay, so what forces is the swinger exerting? Where is the swinger exerting force in this scenario? What part of the swinger's body is exerting force on what thing? Yes, Anais.
I was gonna say the chains. But
Thank you. Right,
really?
the chains. You are pulling and pushing on the chains, right? As you go up, you're pulling on the chains. As you go down, you're pushing on the chains. Are you guys okay with that?
Yeah.
You are pulling and pushing on the chains. But here's the problem. That's part of the system. You pulling and pushing on the chains is not responsible for your acceleration because the chain is part of the system. So that external force is coming from somewhere else. Where is it coming from? Yes?
Well, at first, you kind of like push yourself backwards and you step forward.
Oh, you mean like if there's the ground there? But let's pretend there's no ground there. Yeah, you usually like to start yourself, but you don't need the ground. You can do this without the ground. Someone please tell me, where's the external force coming from?
the pole.
What?
The pole.
The pole. Thank you. The pole, right? Because when you swing, what do you hear? Squeak, 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 squeak. That's the sound of friction, right? That's the sound of friction. It is friction between the way my swing is attached to the pole and the pole. It's that friction that's doing it for you. when you pull this way on the chain, you're pulling this way on that connection, which means that connection's pushing you that way. When you do this to the chain, then that thingy is pulling you in the opposite direction. And by doing this at the correct frequency, at the resonant frequency of your swing, you can swing yourself. It's these guys. If you've ever been irritated by the squeakiness of a swing, well, don't be irritated anymore. That's what's causing you to be able to swing, right? I was an engineer before I became a teacher. I was an engineer, and I had a lot of experience with bearings. So let's say for my cute little daughter, I said, honey, I'm going to build you the perfect swing. I'm going to build a swing with ball bearings. I got to make a better ball bearing. I don't know if this is a very good ball bearing. Yeah, like the fidget spinners, exactly. I'm going to make ball bearings, and then the pole will go through the ball bearing, okay? And the ball bearings would be attached to a rope, and you'll be on there, and it won't make a sound because your chains are attached to these perfect bearings that are utterly frictionless. Tell me, is she going to be able to swing herself now? No way. She'll go like this, then she'll go like that, then she'll go like this, then she'll go like that, and she won't go anywhere. She'll just be shifting her body weight back and forth, but she won't go anywhere. The only thing that this swing is good for is for someone to come along and give her a big push, and then she'll just swinging like a big pendulum. She'll just keep swinging back and forth for 15 or 20 minutes, right? Because it's frictionless pretty much, you know. But then when it's time for her to swing again, someone's going to have to push her again. She won't be able to do it herself because there's not any friction there. You guys okay with that? So again, you know, and there's many scenarios like that where you're asking yourself, where's the external force coming from? Well, it comes from somewhere. You just have to figure out where. All right. Well, hey, now it's time to talk about free body diagrams. I'm going to tell you the stuff about free body diagrams, then I'm going to show you how to do problem number 13, and then we'll be done. You may not be an expert after today, and that's okay. We're going to do free body diagrams day after day after day, and after a while, you'll become experts. After a while, you'll be dealing with incredibly complex situations using free body diagrams. Today's just day one. Free body diagram. Okay. Suppose I have a situation where I've got a big box and I've got this guy and he's pushing on the box. So he's exerting some force on the box F, and the box won't move because friction between the box and the floor is opposing its motion. I want you to make a free body diagram of that situation. Here's the rules. Number one, you do have to define what your system is. You've got to define which object's motion are you interested in. Well, you tell me, which object's motion do you suppose I'm going to be interested in? I haven't even told you. But yeah, the box, right? So you, in your own mind, you have to define what's the object of interest. Which object's motion am I interested in? That's, what's that? Okay. So that's our system. So what I'm going to do is free this body from its surroundings. I'm going to ask myself, okay, what are the forces acting on this body? I'm freeing the body from the surroundings and just asking myself, what are the forces acting on this body? That's why we call it a free body diagram, because it's kind of like you're freeing it, you know, from, you don't care about how it influences the surroundings, you only care about how the surroundings influence it. So here comes the rule. Number one, your system is a big, fat dot. Here it is. There's my system, there's the box. I just draw it as a big fat dot. You don't have to draw a box. If the system was a person or the system was a car, you don't have to draw a person or a car. Just draw a big fat dot, that's good enough. The second step, and I'm gonna go to my notes to remind myself. The second step is to draw the forces acting on the system. You do not care about the forces that the system is exerting on its surroundings. You only care about the forces that the surroundings are exerting on your body, on the body of interest. Don't care about forces that the system exerts on the surroundings. With a free body diagram, think of the system as like the perfect narcissist. I don't know if many of you may know what a narcissist is. That's a person who only cares about themselves. The way they interact with the world is they only care how the world influences them. They don't care how they influence their surroundings. They don't care what effect their actions have on the people around them. They only care about the effects that the actions have on themselves. That's a narcissist. Well, think of the free body as the perfect narcissist. He only cares what happens to him. Tell me, now, what are the forces acting on this box? Good, friction, and that's going to the left. So you're gonna write the force as a vector and label it. What other forces acting on this box? Good, the force I'm exerting, F. What's another force acting on this box? Gravity. We'll have another name for it soon, but we'll just call it gravity for now. And finally, what's another force acting on this box?
The floor.
Say again?
The floor.
Yeah, the floor, right? Look at me. Gravity is exerting 260 pounds of force on me, but I'm not accelerating to the center of the earth. Why aren't I accelerating to the center of the earth? Because the floor is holding me up. Well, the same thing with this box. The floor is holding it up. And we're going to learn soon that we call that force normal force. And you'll see why. So there's my free body diagram. Now, there's one thing I do with my free body diagrams that I care about. It was the way I was taught when I went to college, when I went to Harvey Mudd College. They like to have all the forces emanating from the body. You'll notice I drew my forces where all of them, the initial point is at the body. And I think that that makes it where you're less likely to make mistakes. There's a lot of people who, or even textbooks, who their idea of a free body diagram are some of the forces emanate from the body, some of the forces go into the body, and it's just kind of a mishmash of sometimes they do one, sometimes they do the other. And I just find that students are more prone to making mistakes if they mix up whether they go into or out of the body. I'd rather just have all the forces emanate from the body. Draw all forces, forces as emanating from the body. There's two more things that I want in a free body diagram. And here they are. Or for a free body diagram problem. Number 3, define which way is positive. Ordinarily, we'll say up is positive and right is positive. But unlike kinematics, where we pretty much always defined up as positive or right as positive, with free body diagrams, you'll see more frequently you'll want to define down as positive or some weird angle as positive even for inclined plane problems. So I'm going to want to see that you know which direction is positive, left or right. And normally, I just put it in a little cloud off to the side. Just tells the world, hey, up is positive and to the right is positive. And then last but not least, you're gonna do these problems just like you did those two-dimensional kinematics problems. You're gonna have to consider F equals ma in the x direction and F equals ma in the y direction. That is, you're gonna have to use the sum of the forces in the x direction, which is the same as the net force in the x direction, is going to equal mass times the acceleration in the x direction. And you're going to have to use the sum of the forces in the y direction equals the net force in the y direction, which is equal to mass times the acceleration in the y direction. Okay, let me show you problem number 13. I'll actually do it in its entirety. And then that might be enough for you to do the rest of the homework. And then we'll do this more and more every day. Here comes problem 13. Problem 13, they show me a box. And it's got 40 Newton force acting to the right and a 60 Newton force acting at a 45-degree angle. Well, they put a box there, but you know what I'm going to put? A big fat dot. And luckily there's no one in here named Dorothy, because a nickname for Dorothy would be a dot. Because then I can't say big fat dot, particularly if she were overweight. Which, by the way, none of you guys are overweight. No one in this class is overweight. Wait till you get to be my age, then you'll experience what overweight is. None of you are overweight. Okay, here we go. Big fat dot. That's step one. Step two, draw the forces acting on the system. Draw the forces emanating from the body. I've got two forces. I've got 40 newtons acting to the right, and I've got 60 newtons acting at a 45-degree angle. Those are the two forces. They show a box here. I'm doing a free body diagram. Okay. Next, I'm going to define which way is positive. And as our custom, up is going to be positive and right's going to be positive. There's going to be times when that's not going to be true, but that's true this time. By the way, they tell me this is a 3-kilogram object. So you should know that this is a 3-kilogram object. They want me to find the acceleration, both magnitude and direction. That's the question. It's a 3-kilogram mass, find the acceleration. So last but not least, even on really simple problems, I'm going to be using the x and y components separately. I'm going to treat the x and y directions separately, because I think it's a good habit to get into. So, looking at the x direction, I have the sum of the forces in the x direction equals max. And looking in the y direction, I'm going to have the sum of the forces in the y direction equals may. And by the way, have I had an occasion in this class, have I talked about that sigma, the Greek letter sigma? Oh, my bad. Okay, if you've had statistics, you'd be familiar with it. This is the Greek letter sigma, the capital sigma. So if you went to a sorority named Sigma Alpha Beta or something like that, that would be what the sigma looks like. And it always means in math, sum of, the sum of. So when I say sigma f sub x, I mean the sum of f sub x. Well, hey kids, we're almost done. Tell me, if I'm going to do the x and y components, what am I going to have to do there?
Find the y.
Yeah, and x components, right? I need to find what the x and y components of this 60 Newton vector is. I can't be plugging in here unless I know the x and y components. So that's what you'll always do. When I give you a problem with force vectors at weird angles, you will always get the x and y components. In fact, you can do that first before you do anything else. Here, I need to get the x and y components. That's a 45-degree angle. So this y component's gonna be 60 newtons times the sine of 45 degrees, and just believe me that it's 42 newtons, which means the x component is 42 newtons. So now it's time to plug into my equations. You tell me, what's the sum of the forces in the x direction? How many people are thinking 82? Good for you guys, right? Because there's 42 and there's another 40, making a grand total of 82. I'm gonna write them out, just because you're gonna find that that's the way we do things. So I got 40 newtons plus 42 newtons equals the mass times the acceleration in the x direction. Thank you. So I do the division, 82 divided by 3 is 27 1/3, 27.3 meters per second squared, and that's my acceleration in the x direction. Tell me, what's the sum of the forces in the y direction? Hopefully you guys are saying it's 42. It's not 82, because in the x direction I had the 42 and the 40, but in the y direction all I got is that 42. So it's 42 newtons equals 3 kilograms times a sub y, or 14 meters per second squared equals a sub y. But they wanted the acceleration, both magnitude and direction, so what's the last step I'm gonna have to do here? Everyone thinking Pythagorean theorem, inverse tangent? I'm kind of zipping along here because I'm running out of time. But yeah, the magnitude of the acceleration is going to be the square root of 27.3 squared plus 14 squared, which ends up being, is that square root of 27.3 squared plus 14 squared is 30.7 approximately. And then my angle theta will be the inverse tangent of 14 over 27.3. Because my acceleration is, 20, 27, and then 14. So I got inverse tangent of 14 divided by 27.3. I get 27 degrees. And it'll be north of east. So as far as I can tell, all of tonight's homework can be done the same way. Draw the free body diagram, get the x and y components of any weird, vectors at weird angles, and then do some of the forces in the x direction equals max, some of the forces in the y direction equals may, and then do Pythagorean theorem and inverse tangent at the end. And good luck, and we're gonna do this many, many more days, so if you don't get too frustrated, just give it your best shot, and then we'll learn it more as each day passes. All right. Well, hey, good luck.